This is my grade 12 Medium ISP, the Helping Claw MK2. Here's an image of the completed build, and also here's the image of the old arm, just for a little comparison. Sadly, I won't be able to do a demonstration of the arm working in this video, because while testing the voltage curves for each motor, I made the mistake of running all the motors at the same time, just to test continuity. And unknown to me before that, it caused a huge spike in current draw that caused all of my driver boards to blow and immediately stop working. So I've ordered new ones, and as soon as I get them I will film it working, but right now I don't have a video of it. Although I don't have that video, I do have a simulation of the arm running within the modeling software. It uses a skeleton inverse kinematic system that I used to test the movement before I actually printed the parts. So that will give you an accurate demonstration of how the arm would move. Here is the arm in the modeling software I used. It's called Blender. I'm just going to take you through the movements of how the arm would work. So this is the furthest upper joint, which is able to be rotated like this along the x-axis in this, but it would just be rotating along the middle shaft. I could also demonstrate that you can rotate it along the y-axis here, so that's how the hinge would move in this axis here. You're also able to rotate it along the shoulder joint, so as shown here. These stepper motors are all run off the A4998 stepper motor driver boards. I chose these specifically for their ability to microstep the motors for higher precision, and also, ironically, their ability to handle a higher current for larger motors. Clearly they weren't able to handle enough. I will explain microstepping in a minute, but first I want to explain the basics of how a stepper motor functions and what role the driver plays in that. The stepper motors used in this project are two-phase stepper motors, which is why they each have 4 wires, 2 for each coil, or each phase, VCC and ground. The insides of a stepper I can show here. You can see that there are sets of coils inside. It is also lined with many geared teeth along the edges. These teeth determine the accuracy or steps of a motor. The steppers used in this project, which are also the most common types of steppers, are 200 step or 1.8 degrees per step, meaning that there are 200 of those little gears, or each rotation of a gear is 1.8 degrees. So it can rotate 200 steps around, each step being 1.8 degrees. When energized in a certain pattern, the coils will step the motor either clockwise or anti-clockwise. Microstepping is when you rapidly alternate the coils that hold the motor in between steps. You can do this with a square wave or a PWM signal. This takes a large amount more current, and it also reduces the holding torque at that position because it has to be constantly holding it in between those teeth or in between a step. The stepper motor or the driver that I use, the A4998, can go up to a 1/16 step, so you can have a very, very high precision motor. I use on a few of them up to 1/8 stepping. A major issue I had with this arm was that as the angle of the arm increased, it would require more torque to move the same distance. To solve this, I actually took some data using a very precise measuring tool, which is just a ruler. But I just plotted this data in Desmos graphing calculator to find the best match and get a function out of it, so I could have a function that graphed my data. I used that function, or the best matching function, which turns out to be a sine wave, in my code, so that I could actually alter the step time and fix the torque issues and correct for any gravitational issues. As the arm gets further out from the base, it actually moves more. This solution actually worked surprisingly well, and while I had the arm working, all the movements and all the angles were actually consistent. That was when I was testing it before the drivers burnt out. Well, yeah, that is my second attempt at a robotic arm. Maybe someday I'll do a third, but not for a while.